series, or virtual seminar series, as we're getting used to now. I'm Christopher Yao. I'm Professor of Artificial Intelligence in Manchester. I'm standing in for Magnus Raptry today, who unfortunately can't make it. Just a bit of housekeeping for those who are unfamiliar with Zoom seminars. We'll take questions as we go through the talk via the chat box, but you also have an opportunity at the end of the talk to ask in person via your video connection as well. And I'll try to keep a record of those questions in the chat box as we go through and try to get through as many of them in the question time at the end. So that's the housekeeping. In terms of our actual seminar itself, I'm delighted to be introducing Pearse Keane virtually to our seminar series. Pearse is a consultant ophthalmologist at Moorfields Eye Hospital and an associate professor at the Institute of Ophthalmology at University College London. He's best known perhaps in our kind of forum here today for a collaboration he set up now a number of years ago now with Google DeepMind and now Google Health. And I won't talk too much more about it because I'm sure he'll be covering a lot of that in his talk. I know him more recently through work he's been doing, not just in ophthalmology, but also in trying to think more about the kind of end-to-end processes of getting AI into the healthcare system, from the concepts to its translation and its use and safety and efficacy and things like that. So without any further ado, I'll hand over to Pearse, and thank you for being able to join us today.
Thank you, Christopher, for the nice introduction. And really, it's a great pleasure to give this talk here, and tell you a little bit about what we're doing. Now let me just share my screen, and hopefully that is working okay. So I always feel slightly nervous coming to give talks to data scientists, because I'm not a data scientist myself. I'm an academic clinician. But really, what I'd like to kind of try and convince the audience about over the next 45 minutes to an hour is that despite all the hype around artificial intelligence or machine learning or deep learning or whatever terminology you prefer, that it does have the potential to transform healthcare. And of course, I'm very biased, but I think that ophthalmology is one of the medical specialties that's at the forefront of that transformation, and could potentially be, many of the things we've learned could be exemplars or lessons that we could share with other medical specialties. And really, that's going to be the gist of my talk. So as you've kindly introduced already, I'm a consultant ophthalmologist at Moorfields Eye Hospital. And for those of you who are not aware, Moorfields Eye Hospital is the oldest eye hospital in the world, and it's the largest eye hospital in either Europe or in North America. And in fact, we see twice the number of patients per year as the largest center in the US. Now, at Moorfields, I'm a specialist in the treatment of retinal disease. So ophthalmology is quite subspecialized. And so I only see patients with problems at the back of their eye. And so retinal diseases include things like age-related macular degeneration, or AMD. And AMD is by far the commonest cause of blindness in the UK, by far the commonest cause of blindness in Europe, North America, and in many other countries. Other common retinal diseases that I treat include diabetic eye disease, and diabetic retinopathy is the commonest cause of blindness in many countries around the world in working age populations. Until relatively the commonest cause of blindness in working age populations in the UK as well. However, we have the first national screening service for diabetic retinopathy screening, not involving any AI at all, but that has essentially meant that diabetic eye disease is no longer as common a cause of blindness in the UK. I'm also an associate professor at UCL, and really, I'm privileged to lead a clinical research group which is aimed at the development and the application of artificial intelligence in healthcare. And as I say, using ophthalmology as an exemplar. And then the other thing to say is that I am funded by a relatively recent funding scheme called the Future Leaders Fellowship from UK Research and Innovation. And this really is an amazing scheme because it allows me to spend 80% of my time in research, and the remaining 20% of my time can be clinical. And then the other thing I think it's important for the audience to bear in mind, given the content of my talk, is that I have acted as an external consultant for DeepMind, and I act as an external consultant for the pharmaceutical company Roche and Genentech. Now, just in terms of an overview, I think probably 2/3 of this talk, or at least half, will be on the Moorfields DeepMind collaboration. I'll tell you a little bit about the background and the motivation and the setup and the first results and the next steps in that regard. But then I want to tell you a little bit more about the lessons building from what we've learned from that collaboration. And so in particular, the formation of Insight, which is the health data research hub for eye health in the UK, which is funded by Health Data Research UK. I'd like to tell you what we've learned about data protection and ethics and patient-public engagement that has facilitated a study called the ALS-I study. And then I'd like to speculate a little bit and perhaps be a little bit controversial and give you some of my thoughts about an emerging ecosystem for clinical AI. And this is something that you know, you can feel free to shoot me down in the questions and answers that we have at the end when we finish up. Now, okay, so why do we, aside from the fact that it's kind of a cool area and there's a lot of hype around it, and maybe it's a good area to publish papers and get grant funding, why do we genuinely need intelligence in ophthalmology and indeed in healthcare? Or what is the role of new technologies and innovations, which include AI? Now, this is one of my favorite slides to show, particularly when I speak to other medical specialties outside ophthalmology, because other doctors often think that ophthalmology is kind of a cushy number in some ways. They think of it like a niche medical specialty. But in fact, since 2017, ophthalmology overtook orthopedics as the #1 busiest specialty in all of the NHS in England in terms of clinic appointments. So in fact, nearly 10% of all clinic appointments in the NHS are for eyes, and that constitutes nearly 10 million appointments per year. And if you graph the rate of change over the last few years, for ophthalmology, it's like this. And for orthopedics in second place, it's something like this. And the result is that we are drowning in the numbers of patients that we need to see, for want of a better metaphor to describe it. And so if you go to the waiting rooms in, say, for example, the Manchester Royal Eye Hospital, I'll bet you it's standing room only in a lot of those waiting rooms. We're overflowing with patients. This is a problem not just in the NHS, but the world. Now, the brutal reality then is that there are some patients who are going blind because they cannot be seen and treated quickly enough by an ophthalmologist with appropriate expertise. Now, this was this was illustrated in particular earlier this year with the case that got a lot of media attention in the UK pre-pandemic, so it kind of feels like a different world now. But essentially, there was a case in Southampton of a woman in her 30s who was pregnant and also had advanced glaucoma. Now, glaucoma is a disease where you get high pressure in the fluid of your eyes, and it damages the optic nerve, and any damage that occurs is irreversible. So it has to be really picked up, expediently. Now, this one was pregnant and she had advanced glaucoma, and she needed some sort of urgent glaucoma surgery performed. Now, for whatever reason, and I don't know the details, but for whatever reason, there was delays in that happening, and the woman went blind. Now, you could not think of a more tragic situation than a young mother who has lost her sight, and potentially it could have been prevented if there had been an intervention in a timely fashion. Now, it was that need to kind of avoid preventable irreversible sight loss that led me in July 2016, looking at Moorfields, to initiate a formal research collaboration agreement with DeepMind. And so I guess it's everybody on this call knows about DeepMind, but just to say, DeepMind were founded in 2012. and 2 of the 3 co-founders are alumni of UCL, and 2 of the 3 co-founders are from the UK. And so founded in 2012, acquired by Google in 2014, reputedly for £400 million, and getting a lot of media attention because it was applying artificial intelligence in the setting of deep reinforcement learning to video games. Now, from my perspective, what was particularly exciting about them was that the UCL links, the UK links, and the fact that their headquarters are in King's Cross. So that's just two stops away from Moorfields on the tube. So the proximity was very attractive as well. So I approached them actually in 2015. And really the idea was not rocket science. It was simply that could we take these eye scans that we do, these high resolution retinal scans called OCT scans, and we do more than 1,000 of them per day in Moorfields. I'm sure there's huge numbers being done in eye hospitals in Manchester and other centres. And in fact, we know there is all around the world. But these OCT scans are a 3-dimensional imaging modality that have an axial resolution that is an order of magnitude better than an MRI or a CT scan. They say we're doing thousands of them every single day. And so my idea was, can we feed these to a neural network to output a classification task? And this classification task would be a triage decision. So it would be seeing if a patient needs to be urgently referred to a retina specialist, semi-urgently, routinely referred, or just observed. And in that fashion, perhaps get people with the most sight-threatening disease in front of the people who can take the appropriate actions in the most timely fashion. Now, it was middle of 2016 that we actually formalized with a research collaboration agreement this work, but actually it had begun in July 2015. And so what had happened was, in 2013, 2014, I had been reading in the media about, the hype around AI, reading articles in the New York Times about the great AI awakening, and hearing about the ImageNet challenge and all the advances in computer vision and the like. And I was thinking, how can I find people with appropriate expertise in deep learning to address this problem? Now, the truth of the matter is, back in 2013, 2014, when I started to think about this, I did look for academic collaborators first, and I didn't really have a lot of luck in finding anyone that was particularly interested. And so the eureka moment for me was a file of DeepMind in Wired magazine in July 2015, and reading the part which dealt with Mustafa Suleyman, who you can see pictured here, who's one of the co-founders and was the head of the applied division of DeepMind. And in it, Mustafa said something like, we're interested in using our technologies in healthcare and climate change and energy and, to make the world a better place. And so I basically thought that this is the person that I need to contact, particularly because he was from London and his mother apparently was a nurse in the NHS, and I felt certain that he would know Moorfields. So I found his profile on LinkedIn, and I remember I took out a premium subscription for 1 month so that I could actually contact Mustafa without being connected to him. I sent him a message which said something like, "Hi, I'm a consultant at Moorfields. We're doing 1,000 OCT scans per day. There are people who are going blind because they cannot be seen and treated quickly enough. We should work together to develop a deep learning system to triage these scans. And in brackets, by the way, we're 2 stops away from you on the tube." Now, my timing was good, or I was lucky, or a combination of those, because actually a few days later, I found myself in his office and him asking me all these questions about this potential collaboration. And so I knew we did a lot of OCT scans, and I knew that there was this pressing use case. But actually, when he started asking me, how many OCT scans do you have in total? I didn't really have any good answers. And he said, what proportion of them are patients with diabetes? And I didn't really have a good answer. And he said, well, what are the file formats? Are they proprietary file formats? I didn't have a good answer. And he said, what are the ethical and what are the governance requirements around working together on this? And I didn't really have a good answer. So actually, I had to go away and work with the team at Moorfields to begin to figure out the answers to all that questions. And let me tell you, that is not a trivial task by any means. And that was at least 6 months and maybe even a year of work to even begin to be able to answer those questions. Now, when we did have most, if not all of those questions answered, we can put in place the research collaboration agreement. And that allowed us to be able to share about 1.2 million OCT volume scans with DeepMind. And these were all historical anonymized OCT volume scans. And I'm happy to talk in the questions and answers around if people have any queries about anonymized data and the processes and safeguards that can be put in place for that. The other thing was that we recognized in this collaboration that this was, from the start, this is a potentially very sensitive topic, because this is sharing data, anonymized OCT scans outside the National Health Service with an industry partner. And of course, that's particularly the case if you're talking about an industry partner whose parent company is Google, a multinational tech company. And so we tried to be as open and as transparent as we could be from the very start. And so that included engaging with the Royal College of Ophthalmologists, plus all the major eye disease charities, doing a lot of work on patient and public engagement. But also, since 2016, we've had a section of the Moorfields website which is dedicated to this collaboration. You can see videos and explainers about what the collaboration involves. There's also an FAQ section, and so you can get answer questions such as, do patients have to give their consent for their data to be used? Well, the answer to that is, because this is retrospective anonymized OCT scans, they don't have to give their consent for the data to be used. On the other hand, we recognize that patients may have concerns about this, and so we give the contact details of our information governance office, so that if people want to opt out of the research, they can make sure that their information is not included in any data sets prior to anonymization of the data sets. The other thing is, I guess a lot of people won't necessarily check the website. So we've got flat screen TVs in most of the waiting rooms at Moorfields, and we've got a screensaver that sort of rotates regularly on that. And one of the images that comes up is about the collaboration and saying what we're doing and actually pointing patients in the right direction if they want to learn more. We've also got posters up all around Moorfields as well, talking about not just this work, but the range of clinical research that we do. And then the other thing that we did is we published a protocol for the research in an open source journal before we had done any experiments at all. Now, in fairness, the protocol is essentially saying that we will apply deep learning to an image classification task. It's nothing perhaps unexpected for anyone who's involved in computer vision or medical imaging, but nevertheless, I think that's an important gesture to describe what we're aiming to do. So after all of that background, it was really thrilling for us in August and September of 2018 to publish the first results of this collaboration. And you can see here that there's more than 30 different collaborators on this. And you've got scientists from UCL, you've got doctors and others from Moorfields, and you've got some engineers from DeepMind. And I want to emphasize that this was not simply giving the data to them and then having them come back 2 years later with a paper. This was working hand in glove through the process over a number of years. And the truth is that it would not have been possible to produce this without the input from each of those three groups. Now, it was also very exciting that it was not just published in Nature Medicine, but it was featured on the cover of Nature Medicine. And of course, this being AI, you can't escape the hype around it. And so it was thrilling for us to get global media attention. Now, I say thrilling, and you can imagine how excited my mum back in Ireland was, back in Dublin, to be able to tell her relatives on Facebook about her son and all his achievements, but also just a little bit awkward, because I think, this is the issue about hype around AI. It's kind of a double-edged sword. And what I want to just be clear to people listening, explicitly clear, is that we have not saved the sight of millions of people with this algorithm. And in fact, this algorithm has not yet been used in any real world setting. So if you email me afterwards and say, can I come to Moorfields to see the AI? I'll tell you, well, there's not really much to see yet. And so what I've learned since August 2018 is that there is a very big chasm between actually producing some proof of concept with experimental code and publishing it in a research journal, and actually having something that can be deployed at scale. And that's true in the tech world, but is like probably 100 times truer in a healthcare setting. So I'll come back to that in a few minutes, but what exactly did we do? Well, we essentially had a sort of deep learning framework that consisted of 2 neural networks. On the left of the screen, you can see that we take the raw OCT volume scan, we put that into a segmentation network, and the segmentation network we've trained with about 900 manually segmented OCT volumes, and that creates this intermediate representation, which is then fed into a classification network, which we trained with about 15,000 classification labels. And then so ultimately the output of the classification network is a referral suggestion, like urgent referral, and a diagnosis probability, 10 different classes of typical retinal diseases that you would expect. And the nice thing is that not only do we have those classification outputs, but we have this tissue segmentation map. And that gives us a lot of quantitative parameters about the anatomy of the retinal disease, plus also potentially provides some measure of clinical interpretability, although we recognize that's quite a nuanced area. So here's an example of the algorithm in action. So this is a patient with diabetes. This is a man in his 40s with poorly controlled type 2 diabetes. And if you look at the bottom row, what you can see is the raw OCT volume scan that's fed into the segmentation network. On the bottom right, you can see a figure legend with about sort of 10 or more different anatomic parameters that the segmentation network delineates. And you don't have to be a retinal specialist to figure out that this is a waterlogged retina. So this is something called macular edema. And on the second row, you can see we've created these heat maps for retinal thickness and for intraretinal fluid. And then on the top left, we have the outputs of the classification network. And so we have a referral suggestion, in this case, semi-urgent referral. And then we have a diagnosis probability, in this case, macular retinal edema, 98.5%. And of course, it's perhaps not a surprise that we use ensembles for both the segmentation and the classification outputs. So once we had actually developed the model, we had to evaluate its performance. We did this on a large retrospective data set at Moorfields of about 1,000 patients who had previously presented as new patients to Moorfields and had macular OCT scans done. And as a primary output, we wanted to look at the errors on the referral decision because this was our use case. And so we ran the algorithm on all 1,000 scans, and this is what it got. So it had about a 5.5% error rate on referral decisions. Of course, lower is better in this regard. And so that's good. But actually what we wanted to do is benchmark its performance against human experts. And so we got 8 human experts. Experts 1 to 4 are consultants at Moorfields, and they're retinal specialists. And actually some of them are world famous retinal specialists. And experts 5 to 8 are optometrists at Moorfields who have at least some experience in looking at OCT scans. So we locked them in a room and we told them, okay, give your referral decision on these 1,000 scans, and then compared that to the same reference standard. Now, it's perhaps not a surprise, given what I've already told you, that the algorithm did better than all of the human experts except for experts 1 and 2, where it did a little bit better, but it wasn't statistically significantly better. Now, a key point though that I'd like to emphasize here, and this is perhaps an obvious thing to say to this audience, but a key point is that whenever you see hype around AI beats the best, deep learning beats the best human doctors or something like that, it's very common that when you actually dig into the details, you find that the human expert who is doing a task that they don't do in day-to-day life, or doing a task with one arm tied behind their back. And so in actual fact, the human experts never make a triage decision based on an OCT volume alone. And to make it representative of what they do in real life, we repeated the task, but we gave them a retinal photograph, we gave them visual acuity, we gave them a clinical vignette describing the history. We locked them in a room again and asked them to make the referral again. And so it's perhaps not a surprise that that improved the performance of all the human experts to the point where the top human expert got an error rate of 5.5%. So that was equivalent to the algorithm, but of course the algorithm is using the OCT scan alone. Now, what did it get wrong? Well, I won't go into the details here on the confusion matrices, but what the BBC picked up on was AI did not miss a single urgent case. And there's me, you might recognize, pretending to examine Elaine Manna, who's one of our patients at Moorfields with AMD. Now, an interesting aside is that when we looked at the ones that the best human expert got wrong, and this is a world famous person with more than 20 years of experience, it turned out that in most cases, when we looked, it seemed like maybe our reference standard was incorrect, or at least it was an ambiguous or challenging case. And the interesting thing was when we looked at what the AI got wrong, that was very similar. And in fact, many of its mistakes were probably actually correct. And it was our reference standard that was the issue. So like I say, it's one thing to publish a paper, but it's quite another thing to go from a cool demo to scalable deployment of a machine learning system. And this is a figure that I got from TechCrunch about this issue in the tech world. And like I say, this is even more challenging in a healthcare setting. So we've been working on the technical maturity of the algorithm. And it was great that the team at Google Health were actually able to rewrite the code from the Nature Medicine paper from the ground up to create a cloud-based API that could essentially perform the inference with, in a fraction of the time and with a fraction of the computing power from the original paper. And the nice thing was that in March 2019, we did a live demo of this at Wired Health in London. Now, the other important thing is that we're still working on robust clinical validation of this system. I think one of the things that I really would like to convey from this meeting, and in fact, all the talks that I give, is that I think it's appropriate to combine our excitement about this technology, but also balance that with our caution and maybe even skepticism about its use in patients. Because this audience will know very well that this is not magic, and these systems may fail, and they may fail in unexpected ways. And in fact, work that was led by a close collaborator of mine, Professor Alistair Denniston from Birmingham, showed that actually when he looked at the bulk of the deep learning system, deep learning papers that are out there in the medical imaging domain, the methodology of them in terms of clinical validation left a lot to be desired, and that's probably an understatement. And so, we need to move towards more robust clinical validation. We're starting to do that with the work that we've done, or we have been doing that with the work we've done with, in particular, we're trying to validate on data sets from every continent of the planet. So, if we're diagnosing a patient with diabetic macular edema in London, will we be able to do the same thing equally well in Ghana or in Brazil or in Mexico or in the US or in other countries around the world? And we're cautiously optimistic about that, but at the same time, until proven, I think it's right to be skeptical. The other thing is we're thinking increasingly about implementation. And so I think once you have a system that's FDA approved or CE marked, and once you figured out who's going to pay for it, whether it's NICE or CMS in the US or others, actually you still have the problem of how it's going to be implemented. And so we think about new pathways of care, and at Moorfields we're building a new hospital in the King's Cross area from 2021. And so we're trying to already think ahead, pandemic permitting, about how we can have the flexibility around the pathways that we're generating, because clearly the pathways that we have in place are something from the 20th century and we need to kind of update them. We're also thinking a lot about how we can link the hospitalized services with the community, particularly as OCT scanners are increasingly deployed within community optometry settings. And then also how this can be linked with the home. And so we're involved in a number of studies that are using smartphone applications to do things like measure visual function in the home. And so really the longer term vision is, can we bring world-class expertise from major eye hospitals within the NHS and more broadly into the community and into the home? So patients with these chronic eye diseases, we can often prevent them from going blind, but the problem is they have to come to a hospital and spend hours waiting in a waiting room, often for short consultations. And that is, we could definitely improve their quality of life if we could reduce the requirements for that. So in the next few minutes, I just want to tell you a little bit about a spin-off project that we did with DeepMind. And as ever, this revolves, this is generated from our strong feeling that patient benefit is our North Star. And this is Elaine, who we talked about earlier. And from talking to patients like Elaine, we realized the importance of a number of things. The first is, for the original project, was that she faced problems in getting into the NHS to receive treatment for her wet AMD back in 2012 when it started to affect her right eye. And so this was, in part the inspiration for us to look at this triage. I think what we also then began to think about was something that ophthalmologists will be very familiar with, but this idea that if a patient has developed an eye disease like AMD in one eye and lost sight, they can often become very stressed about the potential development of it in their good eye, because that's when they would really be kind of scuppered in many ways in terms of becoming functionally blind. And so we got the idea, could we use deep learning to protect the good eye? Maybe we could develop a deep learning system on time series imaging data where we could predict the future development of a disease such as wet AMD. And if we could do that, maybe we could prevent it from happening or mitigate its visual impact through the use of intravitreal injections, through the use of tools such as port delivery systems, or through novel and emerging therapies such as gene therapy. Now, with that being the case, in May 2020, we published the next paper from the Moorfields DeepMind collaboration, which was also published in Nature Medicine. And I'd just like to give one shout out here to someone called Reena Chopra. And Reena is an optometrist at Moorfields who's doing her PhD with me at UCL. And she's the joint first author with Jason Yin on this paper. And really a rising star in the field of healthcare professionals engaging with clinical AI projects. And she's one of the key people behind this project. Now, the clinical setup was, we have people with exudative AMD, which is wet AMD, diagnosed in their first eye. They're referred for injections in their first eye. And a unique advantage of having two eyes is that the fellow eye is under observation while the first eye is being treated. So imagine, it's this unique situation where we potentially have lots of scans before an actual event happens. So, imagine a world where if someone has a stroke or develops a tumor, and we had like 100 MRI scans in the build up to development of that, maybe there'd be some interesting things we could predict from that data. And of course, we can do that in ophthalmology. And so the setup was, at number one here, we take the raw digital OCT scan, so it's a single scan, and it ultimately feeds to number 6, which is our ensemble prediction model, which feeds to number 7, which is predicting imminent conversion in the good eyes, 6 months. Now, we take two approaches to creating that ensemble. We use an end-to-end prediction model in number 5 here, which goes from the raw voxels of the OCT scan. And we also use something similar to our 2018 work, which involves an intermediate representation. So we do tissue segmentation, and then these metrics feed into a prediction model. And so we wanted to do the latter because it gives potentially some clinical interpretability, but we wanted to do the former because there may be some information that's lost in the process of doing the tissue segmentation. So we want to be careful about that. Just to highlight, and maybe this is not so interesting for this audience, but some of the demographics around this, had about 3,000 patients with AMD with longitudinal data. It's kind of a big number for ophthalmology and for clinical papers, but a small number for deep learning. If we look at the ethnicity, it was about 55% white, British, and Irish, 33% other or unknown, 10% Asian, and 2% Black. And this is about as diverse a population as you're likely to see, and reflects the fact that certain ethnic groups are much less likely to develop wet AMD than others. And we're quite proud of this also because most of the major studies in AMD have typically been around 98 or 99% white populations, particularly in North America. And really, I think what we're doing is that you really need to take strong account of things like ethnicity to avoid issues of racial bias in these algorithms or reduce performance in certain groups. And that's probably a general point across a range of different AI applications. Something just to highlight, if there's any ophthalmologists listening, which is just that the time when the fellow eye received an injection versus the time when we felt conversion occurred was not the same. And I'll tell you why that's important when I show you some of the ROC curves. And then lastly, the entirety of the data set was 96,000 OCT volumes. And the independent test set that we used was about 5,500 OCT volumes. So just to show you the ROC curves, this is kind of the main, the main takeaway from the whole paper in some senses. The blue line is the ROC curve around our conversion ground truth, and the orange line is around injection ground truth. So when the good eye received an injection, you can see the performance is a lot better for orange than for blue, but in fact, the blue line is the much more clinically meaningful metric. Now, the AUC is 0.745, and of course, there's no way to say it other than that that's not a spectacular AUC. But nevertheless, that neglects the fact that the AUC is not a clinically meaningful metric. So really what you have to do, as you will all know, is pick your operating points in the ROC space and use those to get your sensitivities and specificities and other measures. And that determines the kind of clinical applicability. And so you can choose an operating point that's optimized for sensitivity, which we call a liberal operating point. But actually, for our use case, we're interested in what we call a conservative operating point. And so this was one with 90% specificity. So really what we're saying is that in about a third of these patients, we could tell with 90% specificity that they would imminently convert. Now, given that we're going to propose that we have a clinical trial, where patients at high risk of converting receive some sort of intervention with potential adverse effects, we wanted to optimize for specificity because of we don't want a lot of false positives if it's an intervention with potentials. The other thing we did was benchmark against human expert performance, and this was interesting because actually this was not a task that it was known whether humans could do this, and so it was actually somewhat surprising that the human experts were not too bad at this. They could do it, not quite as well as the algorithm, and also with a much higher degree of variability, which would limit the clinical applicability. The other thing to highlight is the subgroup analysis that we did, and maybe this is of interest mainly for ophthalmologists, but a key point is that in our test set of 5,500 OCT volumes, only about 4% of them actually imminently converted. And so I guess you guys will know better than I will about some of the challenges in training systems when you've got this sort of class imbalance. And even in cases with no drusen, 0.0% converted. Even in the highest risk group, drusen volume 75th to 100 percentile, it's only about a 6.7% conversion within in an imminent time frame. So I think that this is important because I think that I've really begun to learn in the last few years about the strengths and weaknesses of deep learning. And I think, it's pretty clear that deep learning can be very powerful, but, when it's exposed to data that's different from the distribution of its training data, it may not perform well and may make mistakes that a human expert would never make. And so, one of the things that I've come to realize, or at least to hypothesize, is that that AI-assisted clinical trials could be a very powerful first use case in a medical imaging setting. Because of course, in a clinical trial, due to the nature of the inclusion criteria, you can specify that only images from a certain vendor are used, only with a certain scanning protocol, only obtained by a certain photographer with a certain quality, only within the context of a certain disease. And then so in doing so, you can kind of mitigate against a lot of the shortcomings of deep learning when applied in a much more open-ended clinical setting. So just to tell you a little bit about what we've learned from this and building from what we've learned, and this will be briefer so that we can have some time for questions, but at Moorfields, we know that we're producing a vast amount of data, about 1.2 million images at least per year. And so as a byproduct of this work, we've now developed a Moorfields cloud. So we have cloud-based, essentially machine learning pipelines at Moorfields. And so, that's something that I think is going to be very powerful in the future. And we leverage that to actually apply for funding to form what's called the Insight Health Data Research Hub for Eye Health, which we were awarded in October 2019, or began in October 2019 from Health Data Research UK. And this is funding that will essentially enable us to expand what we're doing at Moorfields, move all our data to the cloud, and then work with other partners such as University Hospitals, Birmingham, and other NHS trusts to be able to share what we've learned, both on the infrastructure side and the data side, but most importantly, on the ethics and the data protection and privacy concerns around these use of such data. Another thing that we've learned a lot about is that issues of data protection and ethical approvals and patient and public engagement. And so this has meant that we've actually been able to look at another project, which we call the ALTS Eye study. And the ALTS Eye study is the kind of building on the idea that you can use the eye as a window to the rest of the body. And since 2018, we've known that you can apply deep learning to retinal photographs, and you can look at the photograph and you can say, this is a woman, just using deep learning. And using deep learning, you can predict her age. She's 58 years old. She's a non-smoker. She's not diabetic. You can predict her body mass index. You can predict her blood pressure. And so, if you're skeptical, you may say, well, what's the point of that? There are easier ways to tell if it's a man or a woman than applying deep learning to a retinal photograph. But I think the reason why, myself and others were so excited about this is because I've been a retinal specialist. I've been looking at retinal photos for more than 15 years in obsessive detail, and I cannot begin to tell you whether it's a man or a woman looking at the retinal photograph. So maybe if we can get the right data sets and we can have the right labels for that data set, maybe, just maybe, we can unlock some hidden potential there. And so with that being the case, in the ALTS Eye study, we have linked more than 3 million OCT volumes plus 3 million retinal photographs to something called NHS Digital Hospital Episode Statistic Database, or HES. So we now know we now know all the people who've had retinal imaging at Moorfields, if they've gone on to develop a range of cardiovascular or neurodegenerative conditions. And the numbers are quite, they're in many cases 2 or even 3 orders of magnitude bigger than in big population-based cohort studies such as UK Biobank. Now, I think it's fair to say we're just in the early stages of this. If you'd like to learn a little bit more, we published an article there was an article written about it in The Economist in December 2019. And one of the things, just to be clear about, is that we haven't actually published anything scientific from this at all, because in fact, the reason they wrote the article in The Economist is because it took us 2.5 years to get the permissions to make this linkage. And so it was really exciting that Hal Hodson, who wrote the article, tweeted about us And in the article talks about how essentially we had a very cautious and an appropriate approach in terms of the data protection side of things. My last 3 minutes, just to say, I just wanted to say some hopefully thought-provoking and maybe a little bit controversial stuff about where I think an emerging ecosystem for clinical AI may come. And so much of our initial work has in deep learning at Moorfields has been with industry. More recently, I've been able to work with people like Danny Alexander at UCL and others. But where I'm really excited about is actually clinical researchers being able to engage with deep learning in some meaningful sense. So these would be people who might have, you know, who are academics, but who don't have any sort of formal computer science or data science qualifications. And so I was really inspired in 2017 when I saw this article in the New York Times about building AI that can build AI. And it describes how, you know, all the major tech companies have created automated deep learning platforms. And these are typically drag and drop interfaces that allow people to create their own image classification models. So when we saw that, we got really excited. We said, let's get some public image data sets. Let's get some skin cancer lesions. Let's get some chest x-rays from adults, from kids. Let's get some OCT scans. Let's get some diabetic retinopathy photographs. And the exciting thing was that members of my research group with no coding expertise were able to generate these automated deep learning models that had pretty good performance within just a few days. And these are typically using automated machine learning approaches such as neural architecture search to generate these models. Now, we published this in the Lancet Digital Health in September 2019. And one of my heroes, Topol from San Diego, tweeted that this will be regarded as a classic paper when AI becomes part of every medical school curriculum. So even if we are skeptical about it being used in any other sense, it may have some role in educating clinicians about, you know, how deep learning systems work. Now, an interesting thing that I can't help but just mention to you is that in the review process, the editor of the journal said, one point that we hope you'll be able to address in this revision is to emphasize that these tools will not necessarily replace AI experts. And I couldn't help but smile when I read that, because of course, for the last 5 years, whenever I give a talk about AI to doctors, the eternal question is, will AI replace doctors? And the truth is, 5 years from now, 10 years from now, I'll bet you our waiting rooms will still be busy, but we'll have new problems to figure out. And similarly, for AI experts, I don't think that you're going to solve artificial general intelligence anytime soon, and there's always going to be interesting problems to explore. So nevertheless, I am super excited about automated machine learning because I think it could be a bicycle for the mind, something that Steve Jobs talked about in August 1980 in this advertisement for Apple. And reading this advertisement is amazing because it's going back to a world where the personal computer seemed like a strange concept. And what we might forget is that, you know, around that time, people were skeptical of Steve Jobs, Steve Wozniak, Bill Gates, and others, and had quotes like this from the CEO and the founder of Digital. And at the time, computers were mainframe computers made by IBM or mini computers made by Digital that were used by corporations to do their payrolls, or the military, or universities. And nobody could imagine, why would anybody want a personal computer in their own home, particularly if that personal computer was kind of crappy or kind of limited. And I think what Steve Jobs realized and others was that even if they were primitive, that the users of these would come up with hundreds or even thousands of applications. So when I talk to clinicians, I say, if not you, then who? And particularly clinical researchers. And I say, if you're interested, you can download some free data sets, some public data sets. You can sign up to the free tier of some of these platforms, and you can start to explore this. Now, of course, two major caveats. The first is that you shouldn't use your own institution's data until you have the appropriate approvals. And the second is, and let me be really clear, no one is suggesting that these could be used for care of patients. Because if we have to be cautious about using bespoke state-of-the-art systems for direct patient care, we need to be doubly or triply cautious if we're talking about an automated tool. But there is loads of clinical research applications that you could begin to use this that do not require that same level of caution. So Livia and Sigfrid were the members of my research group who did this. And Eddie is a member of my group who's really become, I think, an expert in automated deep learning. And so we have some other papers in the pipeline, but he's been able to do stuff like train models that have performances comparable to FDA-approved models for things like diabetic retinopathy screening. So I think there's a chance for us to reinvent the eye examination with artificial intelligence. If you'd like to learn a little bit more about this, we had 2 short essays written with, as I say, one of my heroes, Eric Topol, in the Lancet in December and April. And one was on reinventing the eye examination, and one was on kind of like some ideas we had about use of AI in healthcare more generally. My last slide, we're going towards implementation, and that's the hard part, I think, in many cases, or in all cases. I think AI-assisted clinical trials will be a powerful use case. AI-assisted scientific discovery is something many people, Demis Hassabis and others, have talked about. And I think we also may be moving towards a period of democratization and industrialization of this technology. And then lastly, if anybody would like to get in touch, that's my email address. Thank you very much.
Thanks, Pearse. It was a fantastic talk. Really amazing work over the last few years by your group for UCL and Moorfields. Before we get to questions, I was just going to say, I as an AI person, I don't mind being automated out. So I could definitely do some help reducing my workload. I always tell my PhD students, I wouldn't mind if AI could replace me as your supervisor or something and answer your day-to-day questions. We have a number of questions, and a couple of people have asked to ask them in person via video. Ray Chen first.
Hi, hi. Thank you for your talk. It's really interesting. I worked a similar project before to develop the AI doctor algorithm. So personally, I'm not an AI expert, but what my background is more like the machine learning, deep learning, and AI part. So I'm interested to know more about your training data. So for example, how you labeled the data and how you deal with the overlapping labels.
So that's a very good question. I think the truth is we spent a lot of time and effort and money on doing that, and we probably had a group of about 10 optometrists and ophthalmologists working for more than 6 months in a room using tools like ImageJ to manually delineate every cyst on an OCT scan. And it took months, and it took meticulous attention to detail to make that happen. So that's a really challenging process.
Okay, thank you. So have you ever used some photos, some data from other, like for example, websites to add noise to your training data or your validation data to see how well the model work with noise?
I think the short answer is I am not sure, and that really would have been work that Olaf Ronneberger and the team at DeepMind would have been involved much more in than me.
Okay, thank you very much.
Thanks for that question. Ruthu, if I'm pronouncing that correctly.
Hi, thank you, Professor, for a really interesting talk and for sharing your insights and time. I just had a couple questions. One, how do you share and clean the data on the fly? Is it done under a time limit? And also, is reducing the bias you talked about just about increasing data sets from minority groups? And also, can you elaborate on how you anonymize the data that you share? Thank you.
Wow, those are some good questions, but difficult to answer briefly. So I think maybe I'll answer. So the anonymization one, I think we anonymize, so of course we remove things like patient names and dates of birth, and we anonymize according to the standards laid out by the Information Commissioner's Office in the UK. and then we go to that standard, and then we see what else we can do beyond that standard. So for example, we don't share dates of clinic appointments, or if we only have one patient who's like 120 years old, we bucket the ages in some way. And so then we anonymize to the best of our ability, but then we acknowledge that there's always a theoretical risk of re-identification no matter what you do. And so therefore we say, what are the other safeguards that we can put in place? So we put in place contractual safeguards around that DeepMind are not allowed to link the data with other data sets. They're not allowed to try and re-identify the data, et cetera, et cetera. And then we also include opt-outs, and then we engage with people so that we can have a good discussion about what are the risks versus benefits of doing what we do. In terms of the other questions, I think there was again labeling. I'm not sure what to say other than it just takes a year or more of having like lots and lots of people in a room delineating everything. And it seemed to me that actually getting the data to DeepMind out of the NHS with all of the paperwork that I've just described, that is the hard part. It seemed to me that when someone like Olaf Ronneberger and the team, Jeff Defoe and the others, like once they had the right data, within days or within weeks, I would see massive improvements in what they could do. It was the preparation that's hard.
And sorry, just about the bias as well, Professor.
What was that? What was that again?
Just about
the bias. Yeah. I think this is something that people like Luke Ogden Rayner have talked a lot about, and you can identify weaknesses in your data set and then augment the data for certain categories, or you can try and produce an algorithm that is more kind of robust or more generalizable. At the moment, so I don't know too much about the latter. Clearly that's an active research area. Where I can help is the former, and saying if we don't have enough patients who are of African origin for our system, how do we get that data, and what are the implications of that, or what are the cautions around that?
And just to bring things to close, I'm just going to ask this one very quick question on behalf of one of the audience members. One of the concerns when we apply AI to healthcare is the interpretability of the model, especially with deep learning. Please, could you elaborate on that aspect in your projects?
I think that's a really important point. So one second. So basically, I think a key point is, if it's a black box, will it ever be used by a doctor? I would say in some situations, yes, in some situations, no. And I think, imagine a situation where you have an AI system that's telling you to give an injection into someone's eye for a retinal disease. And you look at the OCT scan, and to you, it looks plumb normal. Okay, now, do you give the injection and risk being sued because actually, you've given the wrong thing? Or do you not give the injection and, risk being sued because like the world's most famous, best AI system has told you to do something and you ignore it? Now, if you had interpretability in that sense, so for example, the tissue segmentation maps that we have, you might be able to look in and see that the reason why it's telling you to give an injection is because there's an erroneous segmentation, and then you could have a justification to overrule it, and maybe that would help you in that situation. So I think those are the types of scenarios I could see, but ultimately we don't yet fully know what is acceptable or not acceptable. It's all speculation at this point, I would say.
Thanks, Pearse. And with that, I will need to bring things to a close as we've reached 3 o'clock. So thanks, Pearse, for giving this talk today. And of course, we'll give you the obligatory virtual clap. come accustomed to. Thanks everyone for joining today, and we'll see you soon, I guess, for the next event in this seminar series. But once again, thanks, Pearse, for joining us, and it was a great talk.